Good morning, everyone. I'm Francesco Percassi from the University of Huddersfield, and the title of this presentation is Generating and Exploiting Cost Predictions in Heuristic State Space Planning. This work is a collaboration between the University of Brescia and the University of Huddersfield, made with Alfonso Gerevini, Enrico Scala, Serina, and Mauro Vallati. Consider the scenario in which you have an estimate of the cost of a good solution for an automated planning problem. This prediction can be produced by different sources. For example, it could be calculated by a domain expert, or it could be automatically calculated using a predictor based on machine learning techniques. Therefore, this kind of predictions could be prone to errors, both in terms of underestimation and overestimation. Starting from this scenario, we address the following challenge. How can we exploit a prediction of the cost of a plan in order to improve search performance? In order to address this question, we have made the following contributions in this paper. Regarding the learning side, we designed a domain-independent model to predict the cost of a good quality solution of a given planning task. Regarding the planning side, we have modified a best-first search scheme to make it sensible to an externally provided cost estimate. Since these estimates can be seriously inaccurate, we designed an adaptive mechanism able to cope with inaccurate estimates, avoiding that these adversely affected the search. Let's start with the planning part. In order to create a search scheme which is sensible to an externally provided cost, we started from a common best-first search scheme using two heuristics. The first one, namely H-delta, which is admissible, and the second one, namely H-search, which is not admissible. The search scheme adopted is weighted a star, in which the heuristic term, called HB, is a composition of the following components: H-delta, H-search, and the cost prediction B. In this slide, we present the heuristic HB we proposed. Such estimator was designed with the aim of trying to increase the speed search. HB is calculated from the H-search heuristic, which is multiplied by the ratio between estimate B and the lower bound of n, calculated as Gn plus H-delta n. The multiplicative term is used to discount or penalize the H-search heuristic with the aim of accelerating the search towards those nodes that are close to predicted value B. In particular, the nodes such that Gn plus H-delta are much lower than B are discouraged from being expanded. On the contrary, nodes such that their lower bound exceeds B are discounted. As we point out in the introduction, in some cases the predictions may be inaccurate. In particular, we have empirically observed that when we deal with underestimations, focusing the search around B using the proposed heuristic might penalize the search. To strengthen the approach, we propose the following metric called penalty rate. Penalty rate measures how tight estimate B is, and it is calculated as the ratio of the number of expanded nodes whose lower bound has exceeded the estimate B and the number of expanded nodes. This metric is used to gradually deactivate the sensitivity to the prediction in correspondence with the saturation of penalty rate, making HB become more similar to H-search. In this slide, we describe how we implemented the proposed predictor. Useful information about the structure of a planning instance can be extracted under the form of features, which summarize important properties of the problem. The planning community has identified a broad spectrum of features, which are used to, for example, to predict how long it will take to solve an instance. In our work, we consider 196 features coming from different encoding of a planning problem, pre-processing statistics coming from some relevant planning systems, for example, LPG and fast hour, the search space topology analyzed by Torchlight. We used an extensive dataset of 7,000 instances to train the model, and the training was carried out using the AutoWeka tool. We now pass to describe the experimental setting. We have compared the baseline with our search scheme within the fast downward framework. The search is guided in each case by a couple of inadmissible heuristics, HFF and HLM, of which HFF is made estimate sensible. As admissible heuristic H delta, we chose to use Hmax. As instances, we considered all those coming from the benchmark of IPC 2014 and IPC 2018, which are not used to training the model. As estimates, we use those calculated using our predictor. In this slide, we reported the results we got for each domain, comparing our search scheme, which uses penalty rate, with the baseline, which does not use the estimated cost. For each domain, in particular, we reported the following metrics. Delta, which is a metric that measures the distance between the cost estimate B and the cost of the solution found by the baseline. Score Q and score T are the IPC quality score and IPC time score, respectively, and we reported these metrics for our search scheme using a prediction and the baseline. As we can see in the last row, we got an overall improvement both in terms of IPC quality score due to the increase in terms of coverage and in terms of IPC time score. This is the survival plot in which on the x-axis we have the time and on the y-axis we have the coverage. In this plot we have reported three different approaches: the considered baseline, shown by the red line, and two variants of our search scheme, shown by the blue lines, with and without the use of penalty rate. Observing the plot, we can state that the use of estimate sensible heuristic leads to a better coverage over time. Compared to the estimate sensible heuristic without penalty rate, the use of penalty rate boosts the coverage. The use of the penalty rate has a significant advantage in terms of expanded nodes in instances where we have an underestimation. For concluding, in this work we have proposed a methodology capable of exploiting the cost of an externally provided prediction in order to improve planning performance. Measure contributions can be summarized as: we have designed a domain-independent predictor able to provide us an estimate of the cost of a good quality solution given an instance of planning. We modified a best first search scheme in order to exploit these possibly inaccurate predictions. We have designed a mitigation mechanism to be able to use the proposed search scheme even in case of underestimation. We carried out an extensive experimental analysis to show the effectiveness of the proposed method in a certain configuration. Our future work will consider the use of these techniques in the context of temporal planning and plan adaptation. So, thank you very much for your attention.